Well, hello and welcome to today's lecture. We're going to talk about ensemble models. Specifically, we are actually entirely going to focus on voting classifiers so that we can keep this video lecture kind of short. And I'll create another video lecture where I'll talk about bagging and boosting algorithms. So what are voting classifiers? So let's talk a little bit about motivation behind voting classifiers, and then we'll move into a justification behind sort of why it works, and then we'll talk about Python implementation. Okay, so suppose that you have a difficult question and complex question regarding the coronavirus. So you decide to find one of the best world experts on infectious disease and ask her or him that question. And you'll probably get a very good answer, right? So now, suppose that instead of asking this particular doctor, you go ahead and ask about 1,000 infectious disease doctors around the world. Okay, so they might not be the best doctors in the world, but you know, they're good at their job, somewhat good at their job maybe, and they have some experience in infectious disease. So the chances are oftentimes then if you aggregate the answers of these 1,000 infectious disease doctors into one solid answer, you may get a better overall answer than that given by the single infectious disease doctor. You know. So this is in practice known as the wisdom of the crowds. And this is the idea upon which voting classifiers and ensemble models in general are based basically. Okay, so how do they work in practice? I think this picture here explains it really well. So instead of fitting just a single model, so what we'll do is we'll fit a bunch of classifiers on our training data. For example, you can fit a logistic regression, you can fit a KNN classifier, and you can fit a random forest, okay? And now each of those, so when you have a new instance, each of those will predict something. Okay, so suppose that model 1 predicts 0, model 2 predicts 1, model 3 predicts 0. Now instead of looking at the individual predictions, what we can do is we can aggregate these results. So there's different ways of aggregating these results. So one way is this hard voting. Basically, you just count however many times these different classes appear, and then the final output is the one with the highest frequency, 0 in this case. Okay, and so as we said, oftentimes this actually turns out to improve our model and not only increase the predictive power, but also reduce the variance. And this may seem at first sight a little bit counterintuitive, like how is it possible that the aggregate result is better than those of the individual ones. And there are kind of maybe a few heuristic justifications. Let me mention one before we go into these calculations. So it is possible that, for example, the KNN classifier does a better job on a certain portion of your data set than, say, logistic regression or random forest. And maybe logistic regression does a little bit better on another portion of your data set. So when you combine these results together, then overall you may get a better performance. So another a little bit more tangible explanation or justification behind why this idea works is as follows. So suppose that we have a biased coin. So basically there is a 0.6 probability of coming up heads and a 0.4 probability of coming up tails. Think of heads here as success. So basically, heads reflects the idea of having a model that has a 60% of the time, for example, classifies data accurately. Okay. So obviously, if we run the experiment once, that means if I just flip the coin once, there is a 60% chance of success. Now imagine that we toss the coin 100 times, okay? Then what is the probability of getting a majority of heads? In other words, what is the probability of getting more than 51 heads in these 100 tosses? So we can think of this. So how are we going to model this situation? We can model this. We can think of this situation as a Bernoulli experiment. So basically, if we let x denote this random variable, like the process of flipping a coin, then x follows a binomial distribution where the probability of success is 0.6. So as we know, basically the binomial distribution of as we know, basically the probability of getting k successes in n independent trials when we're dealing with a binomial distribution is exactly this here. Okay. So to answer our question, the probability of getting 51 heads, you just sum up these individual sums from 51 all the way to 100. And now, there's obviously different ways of doing this probability as well. So let's go ahead and write a quick Python function that actually does this computation. And I guess I forgot to clear that. Okay. So from SciPy, let's import the combinations. Okay. So I'm going to define a function with two variables. So n is going to denote the 100 in this case. K in this case is going to denote 51. Okay. So let's instantiate a sum. Set sum at 0. And then for I in range n over 2. So we're going to start, in this case, basically from 0 all the way to 49. And we have to increase the sum. Maybe sum is sum may be a function already defined. So I'm just going to do it as count, CT. So I'm not overriding something. Okay. So then count is going to be so combinations nk plus I, okay, since I started 0, and then times, so the probability of success is 0.6 raised to the power of k, but k plus I in this case, because I want to start at k but then keep going, okay, and then times 0.4, and then n minus k minus I. Okay, so coin toss, let's do with 151 right now. So as we see, if we toss the coin 100 times, then the probability that we'll get a majority of heads is 0.97. Think about it this way now. So suppose that you have a lower level machine learning model that has an accuracy of 60%. So 60% of the time it correctly classifies our data. Now, instead of just running or fitting this algorithm or like this method once, let's say we fit it 100 times, okay? Then what we're saying is that we'll get essentially a 97% accuracy instead. Hold on, you may say, well, that's not true. And then I ask, why is that not true? Well, what is one of the big assumptions or major assumptions here? So we assumed perfect and complete independence of events, which is something that we never have when we're dealing with fitting data and machine learning models, because even when you refit this model 100 times, there will necessarily be overlap. More often than not, there will be overlap on the training data. So yeah, we may not be able to go from 60% to 97%, but the principle, because there will be correlation between our models. However, the principle stands. Oftentimes, we will be able to increase the predictive power by sometimes a significant amount, but sometimes maybe we improve it a little bit, but more often than not, at least we stabilize the model, sort of that we reduce the variability and we make it more robust, which is also important. Okay, awesome. So let's go ahead with the Python implementation of this voting classifier. And I'm going to use the airline data set from before, and I've already, just to save time, since we've done this part multiple times so far, I've already read in the airline data set and I've pre-processed it. So here, I'm just going to import some of the standard libraries. And I'm just gonna keep it here for a little while so that you can, but you may want to pause the video right now and like copy this this code. But we've done this multiple times. So all I'm doing is I'm reading the airline data, pre-processing it basically, and I'm scaling it. Okay, so this is what it looks like. So this is the features. We have 23 features, and recall that this is basically whether a person was satisfied or dissatisfied with the airline service. Okay. So as I just said, the plan is as follows. We are going to individually and separately fit a few machine learning models. Specifically, we're going to fit logistic regression, KNN, and a random forest, and then we're going to aggregate the results. Okay. Before we even do that, since I want to be able to kind of measure the performance of these models on a validation set and see how they do on a set that they never see. So what I'm going to do here is I'm going to go ahead and import train split data so that I put aside a validation set that I can test the performance of my models on these on this set after I have tuned the model. Okay, from sklearn model selection import train test split. Okay, so I'm going to do x trained, x validation, y trained, y validate, train test split, so x, y, and then a test size of 20%. I'm just going to designate 20%. It's okay. We have about 10,000 data points in here. Yeah, so actually what I've done here also, one of the things that I've done is since the airline data set has about 100,000 rows or basically data points, I've decided to only pick 10,000 of those for computational reasons. So, okay, so random state is, let's do, I don't know, 42, 43. Cool, so let's just test what this guy looks like. So it looks like just like that over there. Okay, so let's start with logistic regression. And we're going to use for logistic regression and for all of the other models cross validation to check the variability and the performance of the model. In the actual notes that I will post on the website, I also use a random search cross validation for logistic regression, just to show you another method that you can do. You can search for the best parameters, but in the interest of time here, I'm only gonna do the cross validation. Okay, so from linear model, import random, not random, logistic regression. And I think for now, let me actually import everything else from model selection, import, cross-validate. What else do I need here? So I think I need k-fold as well. Tune the logistic regression, then basically we'll move on to tuning KNN and random forest. So not to waste too much time, I've sort of already done this. I mean, we've done things like this before, so I'm just gonna quickly talk over what's going on here. So we want to go over, let me actually start running this in the meantime because it will take a while. So we want to tune the model, we want to tune the C parameter and the penalties, and we're going to use cross-validation and k-fold to do that. So here is on this res_LG is where we're going to store the cross-validation scores for each of the penalties, basically. So we need 2 for loops, one that goes through the penalties and stores the cross-validation scores under this locked dictionary, and then we loop over the parameters where we compute the cross-validation and then store those in, again, as I said, in this locked dictionary. And then for each, so once I've looped over all the parameters, I store those results into the main dictionary. Okay. Hopefully it looks better now. Okay, much better. Cool, so maybe, so the best model seems to be the one with with a penalty of L1 and a C of 0.11. So that's what we're going to do next. We're going to train a logistic regression with these parameters. 11 and then L1 and then solver. Okay, now that we have trained it, let's check how it's doing on the validation set. So, accuracy score. Let me just do pred LG here so that I don't get confused later if I ever need to reuse it. It's doing 0.878. I don't think this is very good. It's not too bad, but you know, maybe we can do a little bit better. So let's go ahead next and fit a KNN regressor. I mean KNN classifier. Okay, and so for KNN classifier, we're going to keep it simple. We are simply going to check the number of neighbors. So we're not going to do anything more fancy than that. So from tree, no neighbors, KNN classifier, okay. So KNN results, okay, so for I and range, maybe we start from like 1 to 200, but move by 15 or something like that. So KNN cross validation, and then just as before, we only, I guess just as I said, we only check for the number of neighbors, and CV, actually let's do X train, well, train, and CV is KF. And then let's store the results in the KN results. So, so let's do, I guess, K underscore here plus string I. And then cross-validation test score. This probably, hopefully not take too long. So in the meantime, I'm going to create a data frame just as I did before. And then check the head of what it looks like. I guess this may actually take a little while. It sort of makes sense, I suppose, but in any case, once we get the results, we're going to do a box plot in this case so that we can check the variability as well. So let's actually go ahead and do that. PLT figure, fig size, let's do 8.6, or maybe let's do 10.6, and SNS, box plot. Well, now I guess we just gotta wait a little bit, so we'll see. All right, well, so I mean, it makes sense. I guess we've noticed this before, that it actually KNN takes a while because it's computing the distances from each point to its neighbors, and that takes a while. So that's why it's important that once you've trained your models, you actually save them, so that next time you are using them, you don't have to retrain them, but you just load them. So I'm going to show you a little bit later how to save the model. Okay, awesome. So let's just run the box plot. Right, so if we look at the box plot, it seems that KNN with 16 classifiers is doing the best. So let's do that, KNN 16. So we'll just train a single KNN classifier now. Okay, so KNN 16 fit x train y train. Yeah, so this happens fast. So let's do predictions on the validation set. Okay. Let's check the accuracy score. Alright, so it's doing better. So this one is doing, it has a 90% accuracy. And finally, but definitely not, I mean, it's not the least important one. Actually, random forest is probably going to do best. We'll see. So let's check. Let's build a random forest classifier. So for random forest classifier, our sort of goal is going to be to do exactly what we did last time. And since we already did that last time, I'm just going to copy paste that essentially from last lecture and post it here. So Ensemble models, random forest classifier. Okay, so this is essentially the same code as last time, so you feel free to check it out. But okay, a random forest classifier is not defined. Well, let's run that cell first. And again, so the rest of the code is from last time, so I'm going to copy paste that as well. Basically, where I just plot the results. So hopefully it doesn't take too long. But yeah, I mean, we're looping over the estimators and the depths, and so here we're using a max features of 5. Basically, we're only allowing the model to pick 5 to randomly choose a feature. I mean, to choose a feature from 5 randomly chosen features out of the 23 that we have in this case. So, And the number of estimators is going from 1 to 150, and we're moving at a scale of 15 because, as you can see, it's taking a while even as is. Okay, awesome. So let's check the plot. So this is what it looks like. Okay. So it seems like it's doing a little bit better. So let's move down here where we, yeah, so it seems like if we look at the tree depth of 14 and the number of estimators 136, then that's where it's doing probably the best. I don't know why it says R2 score here. It's not R2 score. But anyway, so this is accuracy score. It's not a big deal there, but anyways, okay, so okay, so let's train now a random forest with 136, is it 136? Yeah, 136 estimators. And we are going to do max depth of 14. And one more thing we're going to do is the maximum number of features. 5. We're going to fit as well, so this shouldn't take too long. So let's do predictions on the validation set now. Validation set. So accuracy score. Okay, we're doing pretty well. So the accuracy score for the random forest was 94. That's not bad. So next, what we're going to do is we're going to move to the voting classifier. So the goal is basically going to be to see whether we can improve up on these scores that we got. So it's going to probably be hard to beat the random forest because actually random forest itself is an ensemble model, so it does pretty well. However, we may be able to let's see, actually I think it's going to be tough to beat it, but you know, let's check it out and see what we can do. So from sklearn ensemble models, voting classifier, and let's first just check what we need. So we need estimators. So let's define these estimators. And it has to be a list of tuples. So for example, logistic regression. What did we call it here? Did I just call it LG? Okay, I think it's LG. Okay, LG, and then random forest, and then KNN. So the estimators here is models, and then you can choose whether you want to use hard voting or soft voting. Let's do maybe hard. And you can choose to pick weights. So how do you want to pick weights? Well, since the random forest on its own was doing really well, then maybe you want to weigh that a little bit more. And then maybe the next one should be weighed a little bit more as KNN, and maybe logistic regression should be weighed the least. So let's do this, for example. I don't know, 6, or let's do 5 and 2. KNN is not defined. I think it was KNN 16. Cool. Let's fit this. Okay, so there it is. Logistic regression, random forest, and KNN. Awesome. So let's see. Let's make predictions. Actually, so hold on. So what we are going to do now, it's okay, yeah. Well, so what I was thinking is maybe use these weights as hyperparameters and actually search for the best weights. And that's probably what you should do. But let's try this first and then we can maybe well, hold on. So once we have this voting, once we've defined the voting classifier here, yeah, so we want to look for the best weights, basically. So let's go ahead and use cross-validation. So VCF, and here X train, Y train, CV, I'm gonna do just KF, and I think that's basically what we need for this. Okay. Well, VC, let's just keep it like that. So these are the results that we're getting. Actually, we're getting pretty decent results. So let's just do a box plot. What is that? Okay, so this is the box plot. So it's between 94 and a little bit over 95. So I think it's pretty good. So actually, we're going to keep the weights like that for now and just see how we do in the validation set. So 0.942, what was that we got? So random forests, the score from the random forest was 9415. Here it was 942, well, a little bit better, but maybe not so much better. And I want to show you actually, because I promised that I will show you how to save the model. So let me show you how to save the model. So there's probably a few ways of doing it, but we can use this job lib. And I'm not sure why that's happening. So anyways, some warning. And you actually just dump it. So job lib, okay, dump. And we want to dump, what did we call this model? VCF. And we're going to call it voting class pickup. Okay, so now it's saved. So let's read it in. So my model job lib load. Okay. And now how do I know that this is working? So let's make predictions and check the accuracy score on this validation set. We should get exactly 0.9343. I mean, exactly. So pred my model predict accuracy score, so Y validation pred 943. Awesome. Now I see you guys next time. Thank you for listening.